Hello everyone, my name is Maryam Karimi and I'm going to present software-defined ambit of data integrity for the Internet of Things. In in IoT networks, we have resource limitation in IoT devices, so we have to outsource data. It's data owner's responsibility to verify whether the stored data in the clouds remain unchanged. It can be done in two ways. It can verify the data integrity and existence periodically, or the owner or some trusted or interested third party further required accessing this data, and then wants to change if the data is unchanged. However, the level of this verification may be different under different contexts based on the application requirements. The concept of contextual integrity were defined in Nisselbaum's theory, in which it examines whether the privacy is violated as context changes. We use this concept differently and in a different context. Uh, we propose four methods of integrity verification, and which all consider tools in terms of time, storage, and communication. And these four methods includes nested Bloom filter, hash tree, provable data position, and proof of data retrievability. And we adopt the notion of contextual integrity to extract important parameters that are required to decide which of those four verification methods are suitable for our requirements. And based on that context, and in order to do that, we provide a secure architecture that meets this process requirements by performing an authentication, gathering each partition's context information, and decides the proper integrity verification method by addressing the context requirement. And the architecture that we propose is the integration of software-defined networking and software-defined perimeter. In our scenario, we have a data owner that's like storing the data in the cloud servers, and further, it needs to retrieve the data, or maybe the trusted third party, for example, a healthcare provider, wants to retrieve this data from the cloud to service the owner. So we want to check if the integrity can be managed by data owner and data user depending on the context with the help of software-defined networking framework. In that, we have three important entities. Owner gateway, which is a trust verifier that stores data in many cloud servers and generates and stores keys that can verify in the integrity of data. And we have a CNSCP controller that's responsible for authenticating parties and securing their communication. And we have a trusted third-party UGW that wants to retrieve the data and check the owner of the data and check with the owner of the data and to ensure that the data is unchanged and the integrity of data is maintained. And the UGW is the third party that requested for verification of the data. So it only makes sense that we can trust it. Under these constraints, ADI detects accidentally corrupted, forged, or fabricated data sent to the UGW instead of the original data. In our threat model, we have three elements. Adversary that sends corrupted data to the third party. It can be in two ways. It can be the cloud server that is storing the data, maybe under attack, maybe itself is malicious. And the other way, it can be a man in the middle that sends wrong data to the third party instead of the cloud server. We have a fully trusted owner gateway. Um, well, the data is coming from it, it performs updates, it's secure and trustworthy, and it stores keys. We have a trusted user gateway that retrieves and use the data to service the data owner. And if it's not trustworthy, it can just, without going through a verification hassle, it can just use any data that he wants to harm the owner. So it should be trustworthy. We use data integrity checks should be context based and scoped accordingly. That's what we are presenting. In order to do that, we propose four verification methods. Actually, two of them are proposed by us and are innovative, like Bloom filter and encrypted hash tree. And two of them are provided in the literature, which are provable data position and proof of retrievability. Each layer of integrity verification increases the security or reliability, but at the cost of higher communication storage and time overhead. Contextual integrity, despite its name, has been used to indicate how the notion of privacy may change with context. But this is the first time that we use a layer of data integrity verification. We use it to choose the layer of data integrity verification for stored data in IoT devices in cloud servers. A contextual integrity framework is proposed to determine the appropriate layer of integrity required based on the context, and this framework is the integration of SCP and SDN that meets like the context gathering and action enforcing requirements. As we said, we have four verification methods: Bloom filter, hash tree, PDP, and POR. The trade-off is between security and overhead. Um, Bloom filter and tree are not repeatable. It means that repeatability means that the proof should be different each time. The proof that we ask from the cloud should be different each time to make it impossible for the server to use the same proof for further challenges while it no longer may own the data, and supports an unlimited number of verification. Something we said it's not repeatable, it means that when we want to check the integrity of data periodically. But if there is a third party that is retrieving the data and wants to check the integrity of the data with the owner gateway, then it will be repeatable, even if it's not repeatable in a normal situation in the periodic verification. Uh, the nested balloon filter. In the nested balloon filter, we used a combination of balloon filter and generalized balloon filter. Balloon filter is used for set membership queries. It begins with the arrays of all zeros and hashes, set members using k-hash functions, and each hash function yields a bit in the array. In order to check the existence of element, we again hash that element with all those k-hash functions and check if the bits are already set to 1. If so, it's existed in the element in the set. The issue with this simple Bloom filter is that it has high false positive and it will be saturated over time. So there is another architecture, generalized balloon filter. It's initially filled with zeros and one randomly. K1 number of hash functions change the bit to zero, and K2 number of hash functions change it to one. It limits the false positive, but it introduces false negative. It tends to forget all data over time, and there is a combination of a generalized Bloom filter that's called concatenated Bloom filter, and it improves robustness and capacity. And our proposed nested Bloom filter architecture is here. We first hash the data using k-hash functions in a temporary simple Bloom filter, then hash this one into a concatenated Bloom filter. This two-level architecture helps to reduce the communication cost while verification, and the CBF stored in the client. In the verification process, the user gateway requests for the data from the cloud server, and the cloud server sends the data to the UGW. UGW can calculate the temporary balloon filter and send it to the to the owner gateway, and the owner gateway compares this temporary balloon filter against the concatenated balloon filter that's stored there. In this process, there is no key sharing required. The storage overhead is in the order of 1, and if we want to keep the false positive less than 1, for temporary Bloom filter, we need the size 20 bits is enough. For concatenated Bloom filter with K7, and the size 10,700 bits is enough. So it has a very small amount of extra storage. The time is in the order of kn. K is the number of hash functions, and n is the number of blocks. But in experiments, you can see here it takes less than 1 millisecond in every scenarios. So it's so super efficient. And the communication is in the order of 1, which is actually 20 bits, and that is this temporary balloon filter. The second method that we provide is a hash tree, which is a hierarchical structure for a hash values that verifies the data without requiring any key sharing. We first store the blocks SHA values on keyed SHA values in the leaf nodes, then group them based on their time interval and device ID into some parents. These parents are hashed using HMAC, keyed HMAC, and we keep doing this until we get a single node. For verification, the cloud sends the data and subtree to the user gateway. The user gateway sends the subtree and hash values of the nodes that it received, the blocks that it received, to the owner gateway. This is a subtree. It starts from the node that is required. For example, if we request for node 4 for block number 4, it sends the data along with this subtree. This subtree is consists of node 4 and the path to the root and the siblings of the nodes in the path. The owner gateway used the SHA values that it received to build a new tree and then compare that new tree with the subtree that it received from the cloud. And if they match, the data is verified. To optimize the communication and updating the complexity, we limited the number of children in the subtree to R. There is no key distributions required. It's not repeatable, but it's repeatable when there is a third party retrieving when there is a third party that's retrieving the data. For storing the data, the time complexity is ON for building the tree, and the updating complexity, time for updating the updating time complexity is O log N, um, and is shown here. It's like, for example, 36 I mean, yeah, 36 milliseconds. When we have Wi-Fi, for Ethernet, it's 35 milliseconds, and in one system simulation, it's 5 milliseconds. This Wi-Fi and Ethernet are slower because we use Raspberry Pis as gateways. Verification for each block is taking O log n because we have the subtree and comparison of subtrees. And in experiments, it took 26 milliseconds only. So as we said, balloon filter and hash tree are provided by us. PDP and POR are in the literature. We chose DPDP, in which owner needs to know the intact data still exists. If the intact data is still exists, it tags the data using fully additive homomorphic signatures and store them in a ranked-based authenticated skip list. And the proof is the hash of nodes from the leaf to node and to root node. Um, in POR, it's first add some parity to the nodes, to the data blocks, and then added the tag, and also add the tag to the parity nodes. It's super expensive in storage. Here we compare balloon filter, tree, DPDP, and hail. As you can see, hail is way more expensive in storage than all of them. Balloon filter is the most efficient one, and also in time complexity, balloon filter is more efficient than any of them. And then we have tree and DPDP. And in update, Bloom filter doesn't need any update, and tree and DPDP should update the subtree and proof. Um, and some tags and the storage is shown here, and the complexities for storage are also available here if you need to further information. In order to choose between those four verification methods, we are using contextual integrity. The term contextual integrity has been used to maintain the integrity of context to ensure privacy violations are minimized. We propose the context data integrity uses the right mechanism to verify the integrity of data based on the scope or ambit. And one ambit may need quicker verification, but if there is a potential for mischief, this may be mitigated by changing the ambit. In contextual integrity, we have four main parameters: subject, sender, receiver, information type, and transmission principle. Um, For example, we chose them to extract context information. For example, the subject in our case is the person or the thing that this information is about. So it has merit, a start time, birthday or product date, and functionality. For example, the receiver is the cloud server that we have security, trustworthiness of the server, and a storage price for it. Overall, we could extract these parameters: permission, merit, time, update required or not, affordability, redundancy, trust, and security. Imagine here we have the permission, the data has high merit, update is required, it's affordable to store some metadata, and we need the data for a long time, so we need PDP for this. We choose the most suitable verification method based on the context. We want to choose most suitable verification based on the context and build a decision-making model, use the context information as an input to the model, and decide on the required verification model considering the requirements. And this application required an architecture that gathers context information and provides the flexibility to enforce the proper verification method. We propose an integration of SDN and SDP, which is a suitable secure platform that gathers information, perform contextual decision making, and provide the flexibility for enforcing actions. SDN has a global view and flexibility, and SDP has a unique security features and architecture compatibility with SDN. SDN separates the control plane from the data plane, and when the switch receives a packet, it will send it to controller for decision making and and the controller install a new rule in the flow table. So further, the switch doesn't need to send similar flows to the controller. It has the global view of the network using the standard OpenFlow, and we also add a messenger and an agent on a messenger on controller and an agent on switches to receive even further informations. Um, SDN has some problems. For example, the controller is a single point of failure, and other applications, switches, hosts, and servers may face some cyber attacks and problems. So, in order to fix that, we use SDP, which separates the security plane from the data plane. And it identified and authenticate all network elements using SPA, which are single packet authentications, and are hiding the servers behind the SDP gateway. There are a combination of STP and STN in the literature review. Ours is more complete and more comprehensive. We integrate both controllers into one controller and both switches into one switches. We have initial drop all policies, and we authenticate all hosts, make decisions about packet forwarding, install routing rules in the tables, share updated authorized hosts and services with switches, and authenticate all devices. Uh, First, all switches should be authenticated, and then these switches send a host authentication request to the STP gateway, and application should also be authenticated. When the host wants to store data in server B, so it will send the request to the gateway. Gateway send the request to the STP SDN controller. The SDN STP controller send it to the decision making application, which is here the verification selection application. It will select the verification method. It will send it to the gateway. It will send it to the send it back to the gateway and install the road between these two gateways. They start communicating and relaying communication between host A and host B and server B, um, until the end of the connection, which they close the connection. We took a feasibility study and measure the amount of data, the amount of time that is required to send a request from gateway to SCP gateway to the application and back to the gateway. It took 37 milliseconds on average. We also perform an efficiency study using hospitalized patients with heart failure datasets. Um, it has admission, award, emergency status, occupation, whether the patient died, discharged, or is still in charge, body temperature, blood pressure, etc. In experiments, 1.2% of the data is selected for being evaluated with POR, 65 with PDP, 4.6 with hash tree, and 20% with Bloom filter. As you can see here, ADI is more efficient than using purely PDP or POR in both time and storage. So in this paper, we propose a method to improve integrity verification performance by choosing the proper verification method based on the context. We provide nested balloon filter and hash tree, and we use PDP and POR from the literature. A method that provides the required security. We want a method that provides the required security while consuming only enough resources. And based on the context parameters of the data, its usage. Data and usage, it's using a data decision tree to decide on the proper verification method. For future, we are proposing using signature aggregation to improve the communication complexity in hash tree, and using two-layer Bayesian inference to improve the describing the data, and also creating a dynamic decision-making model. Thank you so much for your attention. And if you have any questions, you can email me at mak322@pit.edu. Thank you so much.